In today's video, we're going to talk about vectors. You may have seen vectors in physics. Before we talk about vectors, we're going to talk about directed line segments. Directed line segments look like rays, okay, but they actually have endpoints. So we might say we have point P and we might have point Q, and a directed line segment would start at one point and go towards the other point, and it would be drawn like this. Okay, so this is directed line segment PQ, and that's the notation. And notice it starts at its initial point, P, and it ends at its terminal point, Q. If we had a directed line segment that was QP, then we would have point Q would be our initial point, and it would go towards point P, would be our terminal point. So when we talk about directed line segments, we talk about having a length because it does have two endpoints. We will refer to it instead as magnitude, and it also has direction. So it starts at its initial point and it goes towards and ends at its terminal point. So it has direction. If you were to find its length for a directed line segment, you would use your distance formula, and to find its direction, you would use the slope formula. All right, now that we've talked about directed line segment, vectors are just the set of all directed line segments that are equivalent. And when I say equivalent, that means they have to have the same length and the same direction. The location doesn't matter. So if we had directed line segments all over our graph, and they all went in the same direction, and all had the same length. That one looks a little longer. Okay, all of those would be vector, whatever we call it, vector U, V, W. Those are usually lowercase, boldface letters. Okay, so it's just all the directed line segments that are equivalent. That's what vectors are. And because vectors are the set of all directed line segments that are equivalent, then we would have to have a way to write all of them. So vectors are written in component form. Okay, so here is component form. So vector V in this case, notice it is got the angle brackets, and it's V1 comma V2. And what are those V1 and V2? Well, vector V in component form, when you were to look at it, it would have its initial point at 0, 0. And its terminal point would be at wherever V1 and V2 were. Okay, so this is vector V written with the angle brackets in component form. So we might have to write component form from a directed line segment. Okay, so I have, let's say I have directed line segment PQ with some point at x1, y1 and some terminal point Q at x2, y2. To find vector V in component form, or whatever you're going to call it, vector U, vector W, what you do is you subtract the x2 minus x1. So notice the order, that is the terminal minus the initial. So we do that for both the x's and the y's. So terminal x minus initial x. Terminal y minus the initial y. So let's try one. So I have a directed line segment RS, and I'm going to write it as vector V. I could have picked another letter, but I used V. And point R, the initial point, and I know it's the initial point because R is written first, and R is negative 4, 2, and the terminal point S is at negative 1, 6. So to write this vector in component form, I'm going to do terminal minus initial, so the x's and the y's. So terminal x minus initial x, terminal y minus initial y. All right, so -1 minus -4, so -1 plus 4. So I have 3, 4 is vector v written in component form. I said that when we find the length or magnitude of a directed line segment, we would use the distance formula. But if the directed line segment is instead written as a vector, then to do the distance, so if it's written as a vector in component form, well, then I don't have 2 points, except I do because my initial point is 0, 0, and the terminal point is v1, v2. So I could still use the distance formula. However, because the initial points are both 0, then when you subtract, you just get v1 and v2. So if you have component form to find the magnitude, we can just use the square root of v1 squared plus v2 squared without having to use the distance formula, because for the initial points, both of these would be 0 if you were using that. Now, if you have a directed line segment, then by all means use the distance formula. I do want to point out that this looks like the absolute value of v. And I mean, technically that's what those symbols are, but that's really the magnitude. Okay, so if you see those symbols, we're talking about the magnitude. And if you think about it, absolute value is the distance away from 0. And that's all the magnitude or the length is how far is the vector, how far does it go from 0 to its terminal point. So that really is absolute value, but that is magnitude, the length of the vector. So let's find the magnitude of vector v, which I have as 2, -7. So the magnitude of v, and I know it's going to be tempting to just take the absolute value of both numbers, but this is the distance formula, or the length. So the square root of, and I'm just going to use this right here, so v1 squared plus v2 squared. So I have the square root of 4 plus 49, which comes out to the square root of 53. If we could simplify it, do it. If the directions say a decimal answer is acceptable, we'll go ahead, but the magnitude of this vector, its length, is square root of 53 units. Okay, so now we are going to look at if we are going to add vectors, subtract vectors, or do what's called scalar multiplication. So if you are going to add vectors together, all we have to do, so if I'm adding u plus v, okay, I could write it out like this. But all we're doing is we're adding the first component number and the second components. So we're really just doing -1 plus 4 and 3 plus 7. So u plus v comes out to 3, 10. So when you're adding vectors, what you're actually doing on the graph, if this helps, I'll draw a little graph here. All right, so we're taking vector u and we are adding v to the end of it. So if I were to have vector u at -1, 3, okay, so there's kind of small, sorry, there's vector u at -1, 3, and then I'm going to add v onto the end of it. So I'm going to go right for 1, 2, 3, 4, and then I'm going to go up 7. 1, 2, 3, 4, 5, 6, 7. So right for up 7, so I have u, and then I added v onto it, and the resulting vector is our answer. So this is u plus v, and if you notice, we ended up at 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we ended up at 3, comma, 10. So that's what we're actually doing when we're adding vectors together. All right, so let's take a look at 3u. So 3u is really 3 times vector negative 1, 3. So it's 3 of them, and we're just going to basically, it's like we're distributing. So we're just multiplying each component of this vector by 3. So we get negative 3, comma, 9. And again, what we're actually doing is we're taking vector u and we're going to add on, we're going to have 3 of those u's together. So we're going to just put end to end, end. So negative 1, 3, and then do another negative 1, 3, and another negative 1, 3. So there's vector u, and then another negative 1, 3, and then another one, and then we end up at negative 3, 9. All right, let's take a look at 2u minus v. So we're doing 2 times u, and then we're going to subtract v, and it is exactly probably what you're thinking. We're going to just multiply the first vector by 2, and then we're going to subtract the components. So negative 2 minus 4 is negative 6, and 6 minus 7 is negative 1. So that is our resulting vector. As always in math, there's always another way to write something, whether it's another unit that you're using or just another notation. So you will sometimes see vectors, instead of being written with the angle brackets for negative 2, 5, you're going to be seeing them with I and J. And instead of writing with the brackets with the comma, it almost looks like an expression. So negative 2 comma 5 is the same as negative 2i, and then 5 is positive, so plus 5j. Okay, it's the exact same vector, just written in a different notation. And then again, if you notice, the I goes with the first component because that's got the number, and J goes with the second component, always. Keep the sign of the numbers, there's no comma, and there are no brackets. So this is the correct notation using I and J.